Okay, we're going to look into coordinate transforms as a more general case of substitution. What we're going to ask ourselves in a two-dimensional case here is that if we had some Cartesian plot with u and v and some figure that we're going to work with, some region G. And so any point in G will be some u and v. And what we want to do is go from whatever the scaling of the UV plane is to the XY plane. And so the XY plane is where we're going to see this manifest itself as some region R in XY. Whoops, X and Y. Now, we can have different coordinate systems that have different scalings, but what we want to be able to do is transform from one coordinate system to the other, back and forth. We can look at the polar coordinates as a special case of this. But let's look at, whoops, I just clicked on the wrong thing here. There we go. Let's just look at having the idea that x can be represented by some function g in the UV plane, and y can be represented by some function h in the UV plane. And we're going to make an assumption that this is a one-to-one transformation that moves between the two planes. So we assume we'll have one-to-one from the interior of G. So R is the image of G under the transformation and G is the pre-image of R. If we get some definitions in here. Any function f of xy defined on R well, that becomes f of g uv h uv, right? We're substituting variables across, and so this is defined on G then. Now, if we're going to look at an integral of f over the region R, then we need to ask ourselves, what's going to be the integral of f over the region G? How do we get this transformation? So let's first think of what happens when we do a single variable transformation. we look at f of x dx, and we're integrating from x equals g of a to g of b, that's going to become from a to b of f of gu times g prime u du, where x is equal to g of u, which means that dx is equal to g prime of u du. Right? A u sub. So what we want to do is get this idea where we'll have some substitution. Again, back up here for this transformation in R. Whoops. For this transformation in R. So we need a derivative factor as a multiplier in the transform. Well, right? We need to, if this is talking about how x and y is changing, just as this was talking about how x changed, and we needed to talk then about how u was changing, we need these multipliers for dx, dy. And so what we're going to use is this thing called the Jacobian. So the Jacobian determinant, or just plain Jacobian, of a coordinate transform x equals g uv and y equals h uv. So the j Jacobian of u and v is the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v, and its determinant. A couple things to note here. If you work with matrices often, columns take on special values and rows take on special values, and so this column space is for the u, right? Here we have the u and the v's, and this row space is for the x, and this row is for the y. So here we have xy vector and xy vector. Here we have a uv vector and a uv vector. So there's just, if you look at the Jacobian, I always looked at it as uv columns, x, y rows. And there'll be similarities for more dimensions. That's one thing we should learn, is as we increase dimensions, our matrices get bigger. Well, a 2x2 determinant is we multiply these together. Subtracted by the reverse diagonal. And so our lovely friends, the partials, have come back. And the Jacobian also gets denoted compactly as the partial of x comma y as a vector, partial u comma v as a vector or a partial function. I see this as a vector because I turn it into this, but again, this is our Jacobian. And what we do then to substitute is we use the Jacobian to help give our multiplying factor. So because the Jacobian is part of a transformation between the two matrices, then determinants determine how coordinate transforms scale. So when you have a determinant of 2, your area is twice as large in your new coordinate system. And what the Jacobian does is give that scaling factor. So if we have some function in dx dy that is transformed with x equals g of uv and y equals h of uv, then in the new, that integral across the region in the new coordinate system is the function g uv h uv times the Jacobian and then du dv. Let's look at an example of a Jacobian we can use. So let's look at transforming a coordinate system where x is r cosine theta and y is r sine theta. And we want to look at the integral in some region r of some function of f of xy dx dy. So let's look at our Jacobian for r and theta. So we're going to look at the partial of x with respect to u, or to r, sorry. It's r and theta, right? X is a function of r and theta, y is a function of r and theta. I'm going to look at x with respect to theta. I'm going to look at y with respect to r, and y with respect to theta. And let's see, so x with respect to r is cosine theta. X with respect to theta is minus r sine theta. Y with respect to r is sine theta. And y with respect to theta is r cosine theta. And if we do the determinant of that, it's r cosine squared theta plus r sine squared theta, or r. So our function over the region will become the function of r cosine theta, r sine theta, r dr d theta. And this is the argument that we got for polar coordinates.